AP Calculus AB, Unit 7, Assignment 6, Office Hours is the pretest for the test. And this is mostly kind of like a review test. This is almost like a retest of previous retests and tests. So a lot of this is like the final without related rates. And then there's optimization. I might split this Office Hours up into all the stuff that's not optimization and do the stuff that is optimization next, because there's a lot of them. Good practice. First problems. This is the actual graph of the function. Find the critical points. Critical points were f prime equals 0 undefined. That's horizontal tangents, by the way, which are clearly at B, F, and H based off the description. So those are all, but also any sharp peaks or valleys will be critical points. So x equals B, E, F, H. So B, E, F, H. Inflection points. I like to emphasize the concavity. Concave up, concave down, concave up, concave down, concave up. So it's where concavity changes, which we're going to assume is C, not D. D is more of a 0. C, E is an inflection point. It goes from concave down to up. So inflection point could be like a sharp corner cusp. F, G. So those are all your inflection points. Relative extrema, that's relative maxes and mins. So we have relative maxes at x equals E, and we have relative min at x equals B and H. So peaks and valleys. D intervals where f decreases, that's where f prime is negative. Also where the graph's going down. So we're going to say A to B, and we include endpoints for increasing, decreasing. We're going to say E to F, F to G, G to H, all 1, 1. E to H. If you split it up, I'm taking out points. Intervals where f prime is increasing. That means the derivative of the derivative, the second derivative, is positive, which is also where it's concave up, which I've already identified. So that's going to be A to C, but we're going to include the endpoints because it says something is increasing. I know we don't include endpoints for concavity, but you weren't asked for concave up. I'm just associating with it with concave up. E to F and G to I. So those are all your intervals where f prime is increasing. Intervals where f prime is positive, so that means it's going up, right? Positive slope, and f double prime is negative. So so this is increasing and concave down. So where's the graph going up and concave down? Going up and concave down. I would say C to E. C to E. It's now to include the endpoints or not. Well, C is the edge of concavity, so we're for sure not going to include it. E is the edge of concavity, so we're for sure not going to include it. Okay. And where else is it increasing and concave down? That may be it. I think that's it. Okay, so that's a big chunk of points there. Just from looking at the graph, do you understand what these things mean on the regular graph? Then we're going to do the graph of the derivative, answer all the same kinds of questions. So the first thing I do is I kind of go through this graph and write a bunch of stuff down. This is where the derivative is negative, decreasing, positive, increasing, negative, decreasing, negative, decreasing. This is a critical point, critical point, critical point. This is a relative going down and up, min, up and down. This is relative max. This is neither. This is a plateau. Then I can go on the concavity graph of this graph. F double prime is positive, it's concave up. F double prime is negative, it's concave down. F double prime is positive, it's concave up. f double prime is negative, it is concave down. So I think, and then inflection points are going to happen where the concavity changes. So I think we got like probably everything. Inflection points at x equals 2, 4, and 5. Relative max at x equals 3. Intervals where f is increasing. 1 to 3 include the endpoints, right? Intervals where f is decreasing and f prime is increasing. That'd be f double prime is positive, which is concave up. So where is the graph below the axis and concave up? So I'd say 0 to 1. We're not going to include 0 because that's the edge of concavity. We are going to include 1 because that's the edge of decreasing, but in the middle of concave up. So we include the 1. And then also, where is it below the x-axis in concave up? So it's 4 to 5. We are not going to include 4 because it is, oh, you know what? We do include 4 because we never said concave up, we said increasing. So we should be including all of these. Tricky. Okay. I'm not going to take a ton of points off, just brackets and parentheses, but try and get as many of them right as you can. Now I have one just like this on the final where I gave you the derivative all done, which you should, I think, enjoy because you don't have to do any derivatives, clean it up. Everything's factored for you. So these are your critical points. X equals 1, x equals -3, x equals 2. Now this one bounces off the graph. This one, you got to solve it. E to the x minus 2 equals 0 is e to the x equals 2. You can take the natural log of both sides, right? And get x equals natural log of 2. We should probably estimate what that is to make sure we put it in the right place on the number line. So natural log graph looks like this, and that's natural log of 1. So it's for sure positive, right? It's definitely positive. It's definitely positive. It's not very big, though, because, I mean, it might be like around 1 or something like that. So hopefully that works well enough for us. So we're going to do a line check. Label your line check. Let's put everything on there left to right, smallest to biggest. -3. See, that's really close. Let's see. You know what? E, what is E? E is 2 point, like, I should have this memorized, 2.7 or something, right? So E is 2.71. So that's a value we should remember, 2.71. So we're saying, what do we raise 2.71 to get to? So it's actually, it's about 1, but it's between 0 and 1. It's between 0 and 1. It's like, it's not quite 1. So that one would come next, natural log of 2, then 1, then 2. Don't forget this guy bounces. Test a value. I like to test far right, usually 3, positive, 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 everything's positive, negative, negative, positive, negative. So we're decreasing, increasing, decreasing, decreasing, increasing. And this is a relative min. This is a relative max. This is a relative min. So we're going to say that there's relative max at x equals natural log of 2. And there's relative min at x equals -3 and positive 2. So maybe we'll have a problem like that on the next test, like you've had on the previous test. You're fine. All right. We have problems like this on the final. This is function analysis. We're trying to, identify different regions or special points, whatever. These problems right here have some typical challenges, okay? All these problems, you should be thinking of domain right at the beginning. Are there any values of x we can't plug into this? If they had even numbers in the bottoms, that would be even roots, and you can't plug negatives in. If they had negative exponents, that'd be division by 0. We can't do that. There are no issues here right now, okay? So increasing, we're looking for f prime to be positive. So we got to find critical points. F prime of x. Be very careful here. 5/3 x subtract 1 gives you 2/3. Minus 20/3 subtract 1 gives you negative 1/3. And we're going to set it equal to 0 undefined. Now you could change the negative exponents to positives, combine these together with least common denominators, things like that. And that would work, but that would be a lot of work. I think it's easier to go ahead and start factoring. You could factor 5/3 out, and then x to the negative 1/3 would be the GCF. The smallest exponent is the greatest common factor. And that's what we always do. But when we have fractions and positive and negative exponents, I think that kind of messes with our head. Now, when I divide this out of both of these, it's going to be x to the 2/3 divided by x to the negative 1/3. Rules of exponents say to subtract it. It's going to be x to 2/3 minus negative 1/3. It's going to be positive 3/3, which is just 1, right? It's just 1. So x equals 4 is the 0. Undefined comes from this guy. X equals 0. If there was an even number in the numerator, that's a repeated root. So these are our critical points. So we're gonna do a line check. Label the line check. If you don't, I'm taking out points. 0, 4. Test a value. X equals 5. Positive, negative, positive. Increasing, decreasing, increasing. Relative max. Relative min. All right. So now we were really looking just for increasing. So that's increasing, that's increasing. So our answer is going to be negative infinity to 0, including 0. We never include infinity. Union 4 to positive infinity. That's where it's increasing. Concave down is where f double prime is negative. So we got to find the second derivative. And our first derivative, I would use this non-factor version. So that's going to be 10/9 x to the negative 1/3 plus 20/9 x to the negative 4/3 equals 0 undefined. So we're going to factor 10/9 out, and the smallest exponent, x to the negative 4/3, and that's going to give you x to the positive 3/3. Works out very nice. Try to make it that way. If you mess that up, things are going to get wild, but you should try and finish to get credit. So 0 comes from this guy, x equals negative 2. Undefined comes from this guy, x equals 0, but it is also a bounce issue because it has an even numerator. That means there's 4 of them. Do a line check. Label it. Negative 2, 0, test a point. X equals 1, positive, positive, negative, concave down, concave up, concave up. So this is an inflection point also, by the way, right? Which you should be able to identify at this point if they're inflection points. If they have that bounce issue, they're not an inflection point. So concave down would be negative infinity to negative 2. We don't include the endpoints. Now, if I ask for concave up, you wouldn't say negative 2 to infinity. You'd have to say negative 2 to 0 and 0 to infinity because we break it up and it's not positive at 0. So we don't include the ends. All right. So be careful on those. There's lots of little mistakes you can make on those, but you've done a lot. 5, find the x-coordinates of the relative extrema. That's maxes and mins, relative, of this function with these endpoints. Determine their nature, like is it a max or a min? So you could just say, well, these are all the relative extrema, which includes maxes and mins together. So we need to take the derivative. It's going to be 2 cosine 2x plus 1. So I'm already doing chain rule in my head nowadays, where I just put the number out front because I'm like, there's going to be extra 2 afterwards. Let's just put it in front where it's going to end up. So we're going to set it equal to 0 undefined. You need to write that. If you're not writing it, I'm going to take off points for that. Anytime you're looking for critical points. So cosine 2x equals -1/2. Alpha equals pi over 3. Quadrants 3 and 2 and 3. You guys should be great at trig. Quadrant 2 is going to be 2 pi over 3 plus 2 pi k. And that's quadrant 2. Quadrant 3 is going to be 4 pi over 3 plus 2 pi k. And I'm always very careful at trig. It's just so easy to make little mistakes. Then I just show all my work. Pi over 3 plus pi k. 2 pi over 3 plus pi k. And so I'm going to get, now we're looking from just 0 to pi this time. So these are critical points. So we're going to do a line check. Label your line check, please. If you don't, I'm going to take off points. Put all these points. Pi over 3, 2 pi over 3. Now there are infinite critical points, so we should emphasize our domain from the problem given to us on our graph. Test a point. Tell me what you're testing. I love to test 0 for trig. In the derivative, not the original function. Cosine 0 is, like, if you plug in the original, you get 0, which should seem weird to you. If we plug in here, we get positive, negative, positive. So this is increasing, decreasing, increasing. This is a relative max. This is a relative min. So we have relative max at x equals pi over 3 and a relative min at x equals 2 pi over 3. Right? Okay, next one, find the x-coordinate of any relative maxima. That's only relative maximums. Some people might confuse it with extrema, but maxima is only maximums. So we need to find critical points. We got to take the derivative. This is a product rule, right? Don't mess that up. X cubed times derivative e to the negative 2x is going to be e to the negative 2x times a negative 2. Don't forget the chain rule. Plus e to the negative 2x times derivative of x cubed is 3x squared. We're going to set it equal to 0 undefined. I mean, we could take an extra step to clean it up if you want. And for some people, that might make the difference of not making a mistake. So just kind of simplify it. But I'm going to factor it. I'm going to factor a x squared e to the negative 2x out of both of them. And then it's going to be negative 2x here plus 3 here. So x equals 0. That's never going to equal 0. X right here equals 3 halves. This bounces off the graph. So these are your critical points. We're going to make a line check, f prime of x. And we're going to have 0. We're going to have 3 halves. I'm going to test a point. X equals 2. Negative. It's going to be negative. Positive. Positive. So this is a relative max. Hopefully you caught that bounce issue because that affects everything. And so we're going to say that there is a relative max at. Don't say the relative max is, because the relative max is the y value, which you could find if you want, but you're not being asked to. We're just asking for the x coordinate. So that's it on that one. For what values is this function decreasing or increasing? Well, let's take the derivative. Now, again, we should be checking domain on all these. What's the domain, especially natural log? The inside has to be great, has to be positive, right? Now, the way we would solve this is we'd say, oh, okay, well, let's find the 0, square root of both sides, plus or minus, x equals plus or minus I, which doesn't mean oh, there's no issues, or it's all bad, or it's all good. You could still do a line check. There just wouldn't be any points on it. And you could test any point you want, like 0, and it's true. And the domain is all reals. Another way to think of it is x squared, no matter what you put in it, positive, negative, or 0, and then add 1 to, is always going to be positive. Like, there's no way to mess it up. But if I don't see any kind of notes in your work about this, I'm going to assume you forgot and you got lucky on this problem, that it didn't have any issues. So we're going to do g prime of x equals 1 over what's inside times the derivative of what's inside chain rule. So we get 2x over x squared plus 1 equals 0 or undefined. 0 comes here, so x equals 0. The undefined comes from here. You should solve it. I want to see that you try to solve it. Plus or minus, x equals plus or minus I, which are not going to be critical points for us, but I want to see it. You do a line check. Putting 0 on there, and test a point. X equals 1 in the derivative. It's positive, negative, decreasing, increasing, relative min. So we want to know where it's decreasing. It's decreasing on the interval negative infinity to 0, and we include endpoints, right? So we're going to include 0. Put a bracket that. We never include infinity though. Concave down, it's the second derivative. We could do quotient rule, low d high minus high d low all over low squared. So that's 2x squared plus 2 minus 4x squared. And let's see, let's keep going. That's going to be negative 2x squared plus 2. Leave the bottom factored. I'm going to factor out a negative 2. That's x squared minus 1. Getting closer and closer. So setting equal to 0 undefined. Undefined would be the bottom. You get plus or minus I, which we're going to throw out. 0 would be the top. We're going to get x equals plus or minus 1. So those are potential inflection points. So I'm going to do a line check. Label the line check. So negative 1 to 1. Test. Let's test like 2. Positive, negative, positive, ooh, negative. Yeah, no problem, children. So it's concave down, concave up, concave down, concave down, concave up, concave down. This is an inflection point. This is an inflection point. So it is concave down on the interval, negative infinity, negative 1. Do not include the endpoints. And then also 1 to positive infinity. And we never include infinity. So there you go. Hopefully getting really good at this stuff. Mean value theorem. So here's the new stuff. This is kind of like the one kind of new thing that we haven't really been tested on. We kind of used it for average speed last semester. But we're trying to find the C values guaranteed by the mean value theorem. That's the place where the actual slope equals the average slope. So we have to find the average slope. So the average slope is just the slope of a secant line between the endpoints. It's a really basic idea. Just draw a line connecting them and find the slope. Now, if we plug 8 in here, let's see, square 9 is 3, 0, 0. So f prime average equals 3/8. They didn't ask you to find the average derivative, but we need it to find this other thing. So then we're going to find the actual derivative. It's going to be 1/2 x plus 1 to the negative 1/2, and we're going to set it equal to the average derivative to figure out where that happens. We could rewrite this a little nicer form. We could flip both sides upside down or even cross multiply. I mean, yeah. So at this point, I would probably multiply by the 3 just because, so I don't have fractions. And then we could square both sides. And so we're going to get 36x plus 36 equals 64. So 36x equals, let's see, I think I made a mistake. Did I make a mistake? No, I feel like it's, you plug 0 into 1. This is a 2. This is 1/4. Oh no, 1/4, and this is 4 over 1. So then we don't need to multiply both sides by 3, and we still have a 2 here, and we have a 4 here, and then we square both sides, and we get 4x plus 4 equals 16, and we get 4x equals 12, and we get x equals 3, and it better be between the endpoints. And if you don't get one in between the endpoints, something else is wrong. Is this a continuous and differentiable function from 0 to 8? Yes, it is. There are places where this function, because it's a square root function, gets shifted to the left. It isn't continuous beyond -1. It isn't even differentiable at -1, has a vertical tangent. But we're good. All right, next one. We got to find the average slope first. So that would be f of pi minus f of 0 over pi minus 0. F of pi is going to be 2 pi sine 2 pi 0 minus 0. And so we get 2. So then f prime itself is 2 plus 2 cosine 2x. And we're going to set it equal to 2, the average slope. Label your work, show your work, show your setups. 2 cosine 2x equals 0. So that means cosine 2x equals 0. And so that means 2x equals 0 at pi over 2 plus pi k, because it happens exactly half the period. Divide by 2, x equals pi over 4 plus pi over 2k. We only want the values between 0 and pi, so that's pi over 4 and 3 pi over 4. Those are the places where the actual slope of the graph equals the average slope of the graph. So that's kind of the new thing. So make sure you kind of understand that. Absolute value theorem, extreme value theorem, we've been doing this a ton. We want to find the absolute minimum and maximum values for this function. So you have the endpoints already, which is sweet. You have the equation. You don't even have to set it up. We need to find the critical points. 1 minus 2 sine 2x equals 0 undefined. You should write all this stuff, label it, write equals 0 undefined. If you don't, take enough points. Sine 2x equals positive 1/2 alpha equals pi over 6, quadrants 1 and 2. 2x equals pi over 6 plus 2 pi k. 2x equals quadrant 2 be 5 pi over 6 plus 2 pi k. We divide by 2. Divide by 2. Get pi over 12 plus pi k. And 5 pi over 12 plus pi k. We only want the values between 0 and pi, so that's pi over 12 and 5 pi over 12. These are our critical points. Now we really want to use a table. We want to use extreme value theorem. So we're going to plug these into the original function, trying to figure out where the original function is biggest and smallest. We need to plug the endpoints and the critical points in order would be good. Plug 0 in, you get 1. Plug pi over 12 in, you get pi over 12 plus cosine of pi over 6 is root 3 over 2. And then 5 pi over 12, cosine of 5 pi over 6 is going to be negative root 3 over 2 because it's in quadrant 2. And then pi cosine 2 pi is 1. Now we should estimate these without a calculator, and hopefully none of them are too close to each other to where it's confusing at all. This is about 0.25, right? That's about 0.25. 3 over 4. So this would be probably about 1.25. And this one's about 3.14, 4.14. Now I got to estimate this square root of 3. So that's between the square root of 1 and the square root of 4. So it's between 1 and 2. It's closer to that one. So I'm going to say about like 1.7. Divided by 2 would be 0.85. So I'm going to guess this is about 1.1. And then this one, we're going to subtract that value. And so I'm going to say this one is about 0.4. And are any of them too close for comfort? I mean, these two are kind of close, so that's a little iffy. But it doesn't even matter because this is your min and this is your max. So we weren't even really considering either of those anyways. So that's fine. So now we're going to say the answer. We're going to write the answer clearly. Now, by the way, they said find the absolute min and max values. They're talking about the y values. They need the y values. But I always give the y value and the x value every single time because it's so easy to mess that up. So the absolute min is, and don't give me these decimals, give me the exact answer, 5 pi over 12. Show me the decimals in your work. Minus root 3 over 2 at x equals 5 pi over 12. And then the absolute max is pi plus 1 at x equals pi. So those are your answers. All right. I'm going to do a separate video for the remaining problems because they are all optimization, and I want to break this video up. So tune in to the next video for the optimization problems.